Welcome to my channel. This video is going to serve as a quick introduction to what I intend to do here and answer a few questions as well about computer chess. So first off, I love computer chess. I'm an avid follower of the computer chess championships, and I always love taking these various engines and using them in high-level Grandmaster games and deeply analyzing the various lines that they spit out. And that's going to be it for this channel for the most part. So it's pretty straightforward, actually, so without further ado, on to the computers. The two engines I'm going to be using for this quest are Stockfish 11 and Lc0. Of course, Lc0 is itself more of a shell than an engine, but to explain that the easiest, let's first take a look at what Stockfish is. The basic design of all these classical engines, the non-neural networks, is they look at a board position and give it a numerical rating based off of material, trap pieces, king safety, space, pawn structure, and other boring stuff that programmers gave weights for. The analysis itself of a single board state isn't extremely useful until we look at the depth. Subconsciously for humans, it's impossible for us to look at a position and our minds not to immediately go a few moves deeper and look at different possibilities. Whereas these classical engines like Stockfish have to rely on these still frames. However, what they lack in imagination, they make up for in raw processing power. Stockfish itself is a program between 2 to 4 megabytes, but it can process thousands of board states called nodes every second with even moderate CPU power. However, because the number of possible chess moves exceeds the number of atoms in the universe, this raw power isn't enough to get us a practical engine. So in steps something called minimax. It's basic game theory that looks at game trees. Essentially, we have a series of possible variations starting at a parent node and ending at a terminal node. Then it chooses which line we can expect to happen if the white side is trying to maximize the board evaluation and the black side is trying to minimize the board evaluation. Another technique is the so-called alpha-beta pruning, which cuts out entire branches of lines, which will clearly never be the best option and never be chosen by one player. And when combined, these two heuristics produce a chess engine that can fit into your phone and still beat grandmasters like Carlsen with ease. Now, though, we turn to Lila Chess. Like Stockfish, this is an open source chess engine, but Lila was created in the wake of Alpha-0, a chess AI that beat out Stockfish 8 in a 100-game match twice. Although there are some controversies surrounding those matches, the fallout gave birth to our baby Lila, and she's been a star ever since. The basic idea of Lila, or LCO, is that a neural network trains against itself for millions and millions of games with only the rules of the game given to it, and the machine learns the best moves for various patterns and structures based off of its chances at success in winning the game. The search pattern is known as a Monte Carlo approach, which utilizes random selections repeated over time in order to eventually weed out an optimal starting point for its board analysis. At first, the games look like random, meaningless maneuvers, but as incentive structures are built into the AI so that the more it wins, the more it rewards good moves, we see that over time it creates its own evaluation algorithm for board states that is extremely powerful. Note that humans have no control like they do with Stockfish, where they can adjust through programming and editing the code the board evaluations based on material or space or other things. But this system with Lila is entirely self-taught by the computer, and it's also rather massive. For comparison to Stockfish, which is around 2 to 4 megabytes, I believe, the current neural network I'm using for Lila that won the 13th Computer Chess Championship in TCEC Season 17, a network known only by its name, 384x30-T60-3010, clocks in around 131 megabytes, and she is a beauty and a monster. She doesn't rely off of thousands of nodes per second like Stockfish, but in fact, on the same CPU power, she's only capable of around 15 nodes per second, 20 on a good day, compared to Stockfish's 1000. Meaning if I want to analyze it in a game, I have to sit back and let a few hours go by. The search method I talked about briefly as the Monte Carlo approach is also known as PCUT, or Predictor plus Upper Bound Confidence Tree Search. This also makes Lila different from Stockfish in terms of its search approach. It takes a parent node and explores a move down that node until a terminal node or a new game state is reached. Meaning that instead of looking at a wide number of various possibilities, Lila goes for depth on a smaller number of total game states in order to find good moves. So far, this has been the most practical and efficient way of using her excellent board state analysis, although this is still an open debate in between AI researchers and practitioners of game theory, so the true potential of this new era of chess engines is truly unknown. This also means that there are some misconceptions about Leela chess. For example, many believe that tactically she's around 3200 ELO rating and positionally she's around 4000 ELO rating, as if a rationalization of her abilities. And while it's true that she did famously blunder a checkmating pattern in a bad position to Stockfish, this PCUT search method also allows for Leela to conquer the horizon effect better than Stockfish does, allowing for her to find great tactical combinations, such as in game 169 of the 13th Computer Chess Championship, where she sacrificed multiple pieces to brilliantly open up Black's king in a Dutch defense daunting gambit line, and get a dominating win over Stockfish, who couldn't even comprehend the tactical threats until it was far too late. Leela does have great positional understanding, though. We shouldn't take that away. Her tactical abilities are still extremely strong also. She found a novelty on move 7 in the Nimzo Indian defense, proving that even in opening theory, she has deep tactical and positional awareness that can beat out Stockfish and human table bases out of the opening. One of the reasons has to do with something called a quiescent search, and it's a problem for classical engines to overcome the horizon effect, which I briefly mentioned earlier. Essentially, engines like Stockfish struggle to see deep ideas since they're brute force machines. Take the game on the screen before you. At first, Stockfish only sees a draw, but after a few more moves, this concept of sacrificing pieces on b6 and creating a new queen is obviously strong, although in this case it might actually still be drawn. But because Stockfish uses a search method that lacks in poor board state evaluations, and it's often incapable of searching beta lines, which are cropped out all too often in the alpha beta minimax search method, these combinations of moves are often ignored where multiple pieces are sacrificed in a row, and Stockfish can miss these tactics. This is also a good hint for when you're playing someone you suspect of cheating and using an engine in Blitz Chess Online. The two ideas are: 1. Lock up the position. Keep the pawn structure closed, and come up with a long-term plan to attack a weak point. Stockfish can't strategize and think, especially at lower depths, and it will just move its pieces around aimlessly in close positions, and in Blitz, with little time for deep analysis, your opponent likely will just move their pieces around randomly, and you'll be able to actually outthink the computer. The second idea is be prepared to go in for an all-out attack where you sacrifice multiple pieces in a row to expose your opponent's king. At limited depth, classical engines often don't assess these beta lines, so you could have a winning tactic that the computer simply hasn't even considered to show your cheating opponent. What I talked about earlier with the quiescent search is the classical engine, like Stockfish, trying to find a non-volatile shift in board evaluations in a line upon which to base its evaluation of a starting node. The more unstable the line, the less likely such a stable node in the board can be found, and the less accurate a board evaluation will be. As an example, whenever you're analyzing a game, have you ever seen your engine go from winning for one player to losing to drawing to winning to drawing, etc., etc.? It's finding the position too volatile. There are too many different lines and possibilities. However, Leela chess with the PCUT search method looks through an entire single line often to the end of a game. And so it does have some shifts, but it's usually far less extreme than Stockfish. Anyways, that's a quick overview of Leela and Stockfish compared to one another. I'm going to try to upload some videos on various games using the engines that'll highlight some of the differences between the engines and also give some good in-depth exploration of some classic games, but I don't have a set schedule set up yet. But anyways, that's the introduction to this channel. Thanks for watching.